long weekend of Thailand. So we are expecting some of this might come soon. In order to make sure that we have enough time to cover all the session, I would like now to humbly request First Visit, the President of IAN, to preside over the opening ceremony. Please.
Dear guest speakers, distinguished guests, ladies and gentlemen, it's my great pleasure and honor to preside over the opening ceremony of today's conference entitled Regenerative Medicine from Bench to Bedside Application. This meeting aims to update physicians, medical profession, and researchers in mesenchymal stem cell therapy, immunotherapy, PRP, growth factors, and cytokines. I'm certain that stem cell therapy will be widely employed in the field of regenerative medicine throughout the world. A lot of progress has been made in stem cell rejuvenation, aesthetics, treatment, plastic surgery, orthopedic application, and treatment of sport medicine. There have been many clinics worldwide offering regenerative medicine services. I feel very confident that Thailand and other ASEAN countries can be the world leader in this field. Finally, I would like to thank everyone for their contribution in organizing the conference, especially Vita STEM International Inc. I now declare open the conference to regenerative medicine and wish for the most successful outcome. Thank you very much.
Today, actually, since there's some rescheduling in the schedule, the PRP and the MSc, so I'm going to combine the PRP and the MSc together to say what is the next level, or how that we can bring this one to the clinical applications. Perhaps while waiting for the slides to be uploaded, just maybe if I can briefly introduce my actual background is actually on embryonic stem cell and liver disease. So I started my work, or the research work is on that particular part where we're looking at the strategy to improve the embryonic stem cell differentiation to the liver, and also we employ the tissue engineering approach to make them mature so it can be transplanted. But ideally, because the project was funded by Geron, or basically that work was done in Imperial in UK, so the project was funded by the company, and they were more interested into the drug development and the screening models. So and we need to have the very mature cell type, so that's where we started to work on the embryonic stem cell. Then I came back to Malaysia and we started with the adult stem cell, because embryonic is relatively quite new in Malaysia, I guess still, and getting the funding for that particular part is quite challenging. But yeah, the government supporting the stem cell therapy as well as the PRP-based therapy, and we got lots of clinical interest on the osteoarthritis, the orthopedic-related application. So then I started to work on the MSc, a little bit on the orthopedic, as well as we do lots of molecular characterization of the MSc, and then the way to culture, the way that to make them more towards a clinic without having a problems, because I think currently the problem with the MSC, people still use a very conventional method that you use a serum from the bovine and so forth, which is contain all the synergenic products. So we try to develop something more clinically approved or certified products. Platelet-rich plasma. One is actually cellular approach, another one is acellular, and quite often we found these two approaches, put it together, they work better. So just to really set the stage, today I'm going to talk a bit on the define the MSC. What is actually the MSC, or the mesenchymal stroma cells, or some people call mesenchymal stem cell. There's differences between the mesenchymal stroma cell and stem cell. I'll talk about it in a bit. And then the property and the culture and manipulation of the MSC in vitro, and also the tissue regeneration by the MSC and how that we can actually bring that to the clinical applications. So MSC, mesenchymal stem cell or stroma cells, both are considered, if you don't isolate or you don't characterize the CD marker, we call them mesenchymal stroma cells. Or if you characterize the CD marker to the purity more than 90%, we call mesenchymal stem cell, because stem cell is being characterized by a set of markers, but stroma cells is just, you get rid the characterization parts. You characterize the mesenchymal stroma cell in the culture, the 2D, and that can be actually called mesenchymal stem cell, because we need to identify the marker in order to call the mesenchymal stem cell. And these cells, ideally, because they are multipotent, their potency is actually can differentiate the cells into multiple lineages, including adipocytes, bone, osteoblasts, tendon, and the merostroma, and they actually go very well into the cartilage and muscle cells. And these are mesenchymal origin tissue type. So before I go into the mesenchymal stem cell, let me explain what is the multipotent is really mean. We call the embryonic stem cell, which is the stem cell isolated from embryo, is pluripotent because ideally they can differentiate to any cell type in your body. But as actually the fetus develop and then the fetus born, or the baby born, and we do have the stem cell in every single organs, including your bone marrow, which is called bone marrow derived mesenchymal stem cell. Your heart actually contains mesenchymal stem cell. Liver has some mesenchymal stem cell. So that tells the mesenchymal stem cells actually supporting the organ function throughout your lifespan. But as you get older, these mesenchymal stem cells also get age, and their regenerative capacity when there's injury in the organ would be reduced, or rather limited actually. So that's the cellular property that characterizes the mesenchymal stem cell. The first one is self-renew. This is the unlimited, or rather we call the proliferation is much more active compared to the somatic cells. For example, once your neuron is actually get injured and then die, it cannot regenerate. The other neuron, post-mitotic cells such as neuron, cannot multiply or proliferate in vivo. But mesenchymal stem cell, they can actually proliferate where there is actually injury. That is what the characteristic we call self-renewal. And they're also multipotent. That means they can go to many cell types actually. If, for example, the tendon is actually injured, and this mesenchymal stem cell in that area can differentiate to provide the tendon cells, the new tendon cells. And one of the very attractive advantage of mesenchymal stem cell is their immunomodulatory activity. If we talk about any of the cell types, especially the pluripotent or embryonic stem cell, transplantation of these cells or adult cells is actually subjected to the immuno-rejections because of the compatibility between the patient and the donor. But for mesenchymal stem cell, because their immunoreactivity is quite low, so the rejection when you transplant these cells is very, very low, and it's a little bit safer than any other cell therapy, as well as the organ transplantation. And another attractive part of the mesenchymal stem cell is it can be easily manipulated for cell therapy purpose. As I mentioned again, revisiting the definition of the mesenchymal stem cell or stroma cells, this is a guideline from the International Society of Cell Therapy. there is a 3 guideline you have to fulfill in order to call them mesenchymal stem cell. Otherwise, they are called mesenchymal stroma cells. So the first one is plastic adherence. So when we got, for example, when we aspirate the bone marrow, we'll plate them on the plastic, the cell culture plates, and whichever the cells adhere on the date, the next subsequent days are actually mostly mesenchymal stroma cells. The hematopoietic stem cell and the other blood lineage related cells will be washed out because they are actually cell suspension based. And the second characteristic is actually we need to characterize whether they have the positive marker for the mesenchymal stem cell, and the negative markers are actually defining these are hematopoietic stem cell. Because we like to draw the attention, hematopoietic stem cell also being used for the clinical trials and so forth. But hematopoietic stem cell differentiation into multi-lineage are much lower. The potential is much lower than the mesenchymal stem cell actually. So that is why the MSC is actually has a very high potential and a good potential, and the researcher would like to explore the potential. And the third one is actually their potential to differentiate at least to these 3 lineages to verify if these cells are mesenchymal stem cell rather than mesenchymal stroma cells. If you don't do these 2 characterization, just by plastic adherent characteristic, we call them mesenchymal stroma cells. So if you see some of the publication called mesenchymal stroma cells, they are mesenchymal stem cells but unpurified or uncharacterized. So the next, I already mentioned about the properties of the cultured MSC. We call cultured MSC because ideally we put them into the plate and we expand them in the culture, then we do the characterization. We don't usually take the cells and then characterize from the beginning because it's loss of cell isolation required before we isolate this particular MSC. And the other parts that I will be talking a little bit more today is the parenchyme effect. MSC is one of the cell source they secrete loss of growth factor, cytokine. This is why when there is an injury in some organs, even the cells don't differentiate to become a particular cell type in that particular organ to replace an injured tissue. These MSCs secrete some good growth factor and cytokine, so the other tissue which is surrounding the necrotic area or the damaged one, they can start to proliferate again. So they produce loss of factor which is induce the proliferation of the surrounding cells as well. In our labs, we are interested, this project we started with a collaboration with a Japanese company that they provide us some of the chemically defined media. As I mentioned earlier, one of the challenge to bring the MSC into the clinical application, especially with the modification of the MSC or the culturing in vitro, is we use the FPS, the serum from the xenogenate product. So this is actually clinically non-acceptable. So there is an interest in my group to use human serum to cultivate. For example, we draw the or we aspirate the bone marrow from that particular patient. We would like to expand them with the patient's serum and put back to the patient, so there won't be any xenogeny or outside product which influence the cell capability as well as any contamination potentially from the other product that you culture. So this is become an autologous, purely on the cell from the patient, and also the culture media or the supplement from the patient's serum as well. So we compare with the standard knockout demand 10% serum and then 10% serum with the BFGF, because we often find having the BFGF in the culture can maintain the stemness or the stem cell property better. And we also compare with the 20% STK because we want to see the combination of media, what the characteristic escape rise, and the STK with the serum STK. And these are the coating that we use to see whether the expansion of the mesenchymal stem cell can be achieved better. So we have the, in our group, I'm collaborating with some of the dentists, so they provide us a sample of the dental pulp. So we actually isolate the dental pulp stem cell because it's quite easy to get that sample, and it's non-invasive because most of the time they actually extract the tooth for some other purposes. And this particular project also, because we are interested to have the MSC and then the secretum of MSC, as I say, the MSC actually can secrete lots of growth factor and cytokine to apply for the hair growth. So this is hopefully we can actually produce a product based on this. So we found basically with the different media, they behave different. Some of the media support the MSC from the decidual tools, and some support the hair follicle. And we found actually the Stem Pro, this is one of the commercially available media, did not support. So there's a need for us to develop a proper media which is patient specific or maybe allergenic based, so it can be applied into the clinics without much of the contamination of the other products. So this is a morphology of the cell that been cultured in the different culture condition, and to our surprise, the STK2, which is chemically defined media, did not really support the MSC proliferation, but not to the level of when you put it up STK2 with the, by the way we call STK because the formulation can't be revealed until they patent the formulation. So the STK2 with the serum gives much more higher proliferation. So that's why we thought rather than using the fetal bovine serum, we can use even the human serum, and they can be actually expanded better. And this is one of the criteria where when we do the transplantation, at least you need to have 10 million cells per transplantation, so it requires lots of cells to be expanded in the culture. And we also found different media actually like influence the heterogeneity of the cells. We actually characterize a marker, as I mentioned earlier, the positive marker for the MSC. So we found that the DBAM, the conventional media only support the 70% of the phenotype maintenance, whereas the STK2 FBS, the one I showed just now, has a very good proliferation, actually indeed maintain the stem cell characteristic better in the culture. So with that, to really come back to how the MSC can contribute towards the regenerative medicine. So why they actually get so much of attention is because MSC can be expanded in the culture without any modifications or any manipulation towards the lineage specification, and the MSC also can be differentiated to a particular cell type. In this case, what in my group, mostly focus, we do both, but we more focus on the cartilage. So MSC can differentiate to become chondro. So that means you can actually provide differentiated cells as a cell replacement therapy. And also, as I mentioned, MSC also secrete loss of growth factor, which can be isolated and then applied for quite many tissue regeneration purposes. And so we know that the final outcome, or what we really expecting, is the tissue repair and the functional improvement. This is rather, I would say, when we have the degenerative disease has progressed, the tissue is die or undergo the necrosis. There's a need for the cells to replace the lost tissue, as well as some factor to activate the endogenous cell itself, so they can proliferate, recap the space that is actually lost the tissue. So that is what the mode of action for the MSC is: either they provide the cells to replace the cells that died, or they actually can reconstruct the structural parts of the organ, for example the liver. So once you actually remove the liver for some disease purposes, you can actually have the MSC transplanted, or MSC to support the hepatocyte growth in the in vivo. And the other modes that people are quite interested is at the paracrine effect, as I said, the host, stimulate the host regeneration program, where the chondrocyte can proliferate when you have the MSC that secretes all the secretome, and also clearance of the necrotic tissue and ECM remodeling. Because we also would like to mention that MSC produce loss of factor, which is promote the inflammation, induce remodeling or the restructuring of the re-clearing of the necrotic tissue, and then ECM remodeling. So it can be same time activate the cells to proliferate, as well as actually remove the dead cells and the extracellular matrix remodeling. So this is, I would like to actually mention here, the MSC derived secretome is quite similar to the PRP way of the plasma rich, platelet rich plasma based therapy, because the platelet-rich plasma also contain lots of growth factors, which is activate the tissue regeneration. So as I mentioned, MSC is a cytokine factory, so you can actually isolate the MSC, expand, and you can precondition some of the MSC to secrete certain growth factor in much more higher amount, and then you can actually inject the secretome for various tissue to be regenerated. And the factor contributing to the secretome profile, so this is what we study in our lab as well. We actually take the age and the younger donor to see whether there is a difference between the secretome of the age and the younger donor derived MSC, and we're also looking at the cell source, as I mentioned before, the hair follicle stem cell condition media and the MSC from the testicular teeth derived condition media. Is there any factors different? The media used to culture, as I mentioned before, the different media induce different proliferation of the MSC, therefore induce different level of the growth factor secretion. And the passage number that I'll show the results in a bit, and the freezing method and the storage duration, because ideally anything that we are producing we are able to freeze, and when we reconstitute back, the growth factor or the MSC should really retain their activity. So that's one of the things we are checking as well. So this is one of the example that we take the STK2 cultured MSC and we look at the passage 3 and passage 4, because at this passage the MSC has the highest proliferation, and when they have a higher proliferation they're able to secrete the growth factor much better than actually they undergo senescence after passage 10 onwards. So we found lots of growth factors that are relevant because the students working on the hair growth application, so she looked at some of the growth factor which is relevant to the hair growth, which is especially over this side where the HGF and the VEGF, BFGF, TGF beta, all these things like regulate at different phases of the hair growth. And we are looking at the factor that activate the telogen phase of the hair growth. So profiling of these cells and looking at how the population doubling of the cells in a different media. For example, here I use the STK2 media, and then we culture the cells, and to see this, the media can maintain the cells very well, and some media may be not able to support because the time and viability actually quite differ over the two different cell types. This is hair follicle stem cell, and this is the dental pulp stem cell. So profiling the secretome and characterizing them, and then potentially we're able to identify what is the right passage, what is the right condition for them to grow and produce a growth factor which is favor a tissue regeneration. And in this case we are looking at the hair growth. We also potentially want to look at the different cell type or different organ failure, and then how that this particular cocktail can help the tissue regeneration for that particular cell type. So the next is actually to checklist for the safety and safety of the MSC for the clinical application. So we know we do lots of manipulation in the culture. We try to make it all the chemicals or the supplements to be clinically graded, and it's not going to cause any side effects or safety problem. The checklist start with the genetic stability of MSC. We don't do at the moment because we haven't tried the clinical trial yet. But one of the criteria that require for you to actually, before you transplant, you have to check for the genetic instability, because you're actually culturing them in the flask, and anything more than passage 10, it will usually the genetic stability will be start to drop. So just in case, this shouldn't really a cause to form the tumor when you do the transplantation. And the cryopreservation and banking of the MSC, there's also a group that we are working together to see what are the methods for the cryopreservation that can retain the cell viability as well as the potential once you actually take them out from the liquid nitrogen. And also we try to have something that non-xenogenic derived cultivation media, including the serum-free cultivation. But at the moment it's a bit difficult. Without the serum, MSC, the attachment of the MSC on the flask or the culture dish is actually very, very low when we don't have a serum. Because serum is a factor that making the cells to attach better on the culture dish. So we can't avoid the serum, we can't go for the serum free at this moment. We are still developing the protocol, but we potentially we would like to go for the human serum so that it doesn't really cause an immunogenic problem. But again, if we look at the FDA guideline or the anything that can go to the human, you should really minimally manipulate. So we need to decide how, to what extent we're going to manipulate, and is this safer? And potentially people are looking at, can we not to differentiate the cells so that it's minimize the non-specific differentiation. So just take the cells, expand in the culture, and put back to the patient. So that is one of the things the researcher need to really decide, how, to what extent we're going to manipulate the cells, and whether autologous or allogeneic, that is another part that we need to decide as well. Is this going to be autologous? Autologous is the best option, but it might not working for all the patients, because if you talk about osteoarthritis, most of the patients we're working is quite elderly people. So when you actually aspirating the bone marrow MSC is not really recommended for them because they are due to the aging and so forth. But taking the cells from them, usually we found the aged patient MSC actually has a less capacity to expand it because of their native aging, the biological aging that occur in the patient as well. So in this case, the one best option here is the allogeneic. But again, also for the orthopedic application, we are developing a protocol where we capsulate the cells. I'll talk about it. I'll show you the example of the results for that. We capsulate the cells into the alginate, so the alginate is actually quite inert, so we can actually transplant to the knee, and that would be more safer for the allogeneic purposes. So the current challenges in developing effective cell therapy, stem cell therapy, is a heterogeneity, inherent differentiate potential of the stem cell, because as I say, different patient has a different aging and the factor, the physiological level and so forth. So the stem cells are actually being affected because of the biological factor, and also heterogeneity of the disease progression. For example, we can't use for example, PRP therapy won't work for the osteoarthritis patient with the complete cartilage is already damaged, because there's no cells, so PRP cannot be a therapy for that. So the disease is actually quite in a different stages determine whether can he use the MSC cells or not. And also the homing and targeted stem cell therapy is because the different mode of your stem cell injection, it's not always the direct injection, or for the articular cartilage repair we do the direct injection, but maybe for heart disease we do a different modes. So this is also another problem when you do the injection, is this stem cell can be directed to the tissue that injured, because more often when we actually do the injection, the intravenous sometimes the cells might ended up in the lung, which is not the place that they're supposed to be, because you need to do the priming of this stem cell, because for the bone we do the SDF priming, so the cells start to express a marker, the receptor on the MSC, so they can be targeted to the particular organ more effectively. But again, this one is a manipulation of the MSC. So that is all we need to decide, whether this is the homing is efficient, we can home to where the cell required, and how to target the particular organ with the stem cell delivery. And the complexity of mechanism of action with the cell therapy is lots of things happening in your body, and you can't expect you inject the MSC into your knee when you have the very severe osteoarthritic knee, you inject that, it might not going to give you a positive result because the area is already inflamed. So with that condition, you actually put it up, the MSC might be a quite a non-effective way. So we need to do a cold treatment of reduce the inflammation, and as well as you do the transplantation. So there's a lot of different procedure involved when it comes to the MSC and how the MSC can work. So you can actually refer to our paper. We actually publish a review to find out what is the right steps and what are the consideration need to be given for us to develop the stem cell to the therapy. And these are the strategies to increase the efficacy of the stem cell therapy. Maybe I just go to the slides. As I mentioned earlier, we can either process the stem cell with maybe co-admin the stem cell with another cell type, because sometimes this is quite useful when it comes to when you have a organ, like a cell type organ, like liver has 7 different cell types. So when you do actually have a damage, rather than transplant the MSC alone, you might need to transplant with some other cells. So actually they work together better. But for osteoarthritis, it's more rather like MSC straight and without any other cell type. So it depends what is the disease that we are looking at. For certain things, MSCs alone is enough. Certain other diseases, co-culture or co-transplant together with the other cell type is quite useful. And again, this is a manipulation of different various culture condition, whether you want to use it, small molecules, drugs, hypoxia condition, because cell culture in a hypoxia condition with the oxygen level very high, low oxygen level, induce the stem cell capability in much better way. So that is one of the area that one of my collaborators working on, and we would like to see whether this condition will actually cause any genetic instability, because at the end of the day, anything that we do, the manipulation, we need to make sure the cells is not transformed into becoming cancer cells. And so with this precondition, and then maybe it's a choice of a different cell type, then we can actually put it into a different dose dilution and then the concentration of the cells, and then we have a different route of delivery route, and we need to really look into which is the best method, or which is to give you the best homing and repair capacity. So for example, delivery of the stem cell for the heart purpose, the direct intramyocardial injection through the epicardium is one of the most effective one, because it's direct to that particular tissue. But again, some other disease might not really can go with the direct injection, something like that. So it's highly dependent on the organ type, which organ we are actually talking about. Here, maybe I quickly go through, since I think the more interest on the clinical application, these are the things we are actually make sure all these characteristics or the parameter being tested, validated for that particular therapy, so we know that how the stem cell can actually contribute to the tissue regeneration. For example, the viability is one of the things we always need to check before you inject, because the stem cell therapy works based on the number that we injected. Too low, it might not gonna give you a very effective therapy. Too high as well, the homing or target organ might not gonna receive all the cells either. So we have to be careful with the viability, and the cells that we actually inject is not the number, but it's the viable cells. And also we need to really look at the severity of the condition, and what is the area infected, is actually whether it's inflamed or not. Those are the things we need to really make sure. How is the clinic, or how is the disease condition, and how your MSC going to be incorporated into the tissue. And the other part is actually the site of infusion. As I said, is quite critical for us to know where we can actually, how we're going to actually deliver the stem cell, as well as the potency of MSC. Would like to remind here, not all the organ failure can actually go for the MSC transplantation, even though MSC is very wonderful. For example, fibrosis, liver fibrosis, when we inject the MSC, it might sometimes worsen your liver fibrosis, because it starts to produce all these secretory function, where the secretome or the cytokines or the growth factor that's secreted by the MSC can even worse the fibrosis, because it activates all these fibrotic cells to be more proliferative, and that might give side effects of the increase in the fibrosis. So we need to look at which disease we are treating actually. So at the moment, there's lots of clinical trials going on with the mesenchymal stem cell right in various countries, and the larger interest is the musculoskeletal diseases, because of the nature of the mesenchymal stem cell that actually can go to all these orthopedic related tissue much higher. So there's a big interest on that as well. Ischemia is another part where we also have a team working on these parts. They are able to show those limbs that need to be amputated is actually can be recovered with the mesenchymal infusion, or actually the delivery of the mesenchymal stem cell. And this is one of the quite successful case, but they haven't started the clinical trial for that one. This is just based on a few case study that we conducted in our hospital there. Central nervous system, this is quite interesting area where the MSC won't be differentiated to become a neuron, but rather they actually try to study if you inject the MSC to the spinal cord, when you have the spinal cord injured, and you inject that, is secret loss of the growth factor, which is suppress the inflammation to some extent, and also activate the cells to attract the cells towards the tissue regeneration, the spinal cord. And they actually proven this one in a mouse model where the motion of the motor neuron activity is much better when you inject the MSC. And I'm not very sure, whether that's been proven with the human already, but I'm quite sure that lots of clinical trials is going on with that part as well. And so this is one of the, again, the review article that we published. So just to recap how that MSC can be useful to become a cell therapy. So we isolate the cells, we can either cell bank for the future usage, something like most of the company can actually offer you the service for the stem cell banking, and you can use it for the further utilization. Or you can also manipulate them in the culture, cell expansion. Here I put it here, reprogramming, because I also work on the iPS, induced pluripotent stem cell. As I mentioned earlier, because I work on the embryonic stem cell, but we actually moved to the iPS to see how to develop the model for the disease modeling actually. So we worked on that part as well. But for MSC purpose, we can actually do the cell expansion, and also if we decided to do the cell banking, again we need to do the quality control of the product and the stability during the storage, and you actually need to do the reviving at the different time point. We usually check at 3 months and 6 months to see whether they actually, for this throughout the 6 months, that particular protocol, the banking protocol, is actually working or not. And also, if you decided to manipulate further, because that's why I say if you decided to minimally manipulate, you can actually take the cells, expand the cells, and inject back to the patients. Or if you decided to actually manipulate them, you can expand them, differentiate to the particular cell type you're interested. And also, again, if you want to go for the product development, you have to check the quality of the final products, and these need to be checked for the purity, potential, and genetic stability, because as I mentioned earlier, you don't want to have a teratoma formation later, and also the functionality, because sometimes when you actually do the preservations or you actually do the manipulation in the culture, the function or the potential of the MSC goes down. So then if you decided to manipulate the cells, again you need to decide whether what is the mode of the delivery, and this is need to come up with a clinical follow-up. And for the animal model, because we haven't tried the human one, the animal model usually we look at this 3 and 6 months for the knee repair to see whether they improve the tissue replacement parts. But for the human, we need to decide whether it's going to be single dose or multiple dose, and what is the interval between the doses, and also how many cells. And ideally, it should be 10 power of 6 cells per kg. It depends on the body mass, the size of the particular person as well, because you can't actually inject 2 lethal cells for a person with a higher BMI actually. Right. So with that, they can actually use for many different degenerative diseases. I'm going to touch a little bit on the osteoarthritis. We have quite a few projects going on there. So on the cell-based therapy, we know osteoarthritis because the cartilage is actually degenerate as due to various reasons. And one of the very obvious one, but people always linked up to the obesity-related osteoarthritis, which is we also study that one, the linking between this one through the leptin expression, and then that induced the degradation of the cartilage. And it also can be caused due to the injury, age, and the genetic. You may be predisposed to the osteoarthritis because of your genetic. And the current treatment is actually total knee replacement if you undergo if your cartilage is already damaged to the full. We also the cartilage also can be for the focal cartilage defect, for the sport medicine related injury for the cartilage. It also can be take the cartilage from one side and then transplant it. So that's the current therapy available. But people are looking into the cell therapy base. So this is what I mentioned earlier. So the very healthy cartilage, when you have all this damage because of the mechanical injury, inflammation and aging, the cartilage they actually started to degrade, and that is the total loss of the cartilage. At this point, some of the therapy won't be working, so that's why you have to go for the total knee replacement. So how does the MSC can work? We can actually take the MSC, expand, put into the scaffold, so they can actually encapsulate it and deliver to the defect area. Or MSC can be actually harvested, expanded, and then also can actually, we can do the intra-articular transplantation directly. But the only problem here, the homing of the cells to that particular cartilage defects area is quite poor. That is the reason why people put into the scaffold, so they can actually deliver, and then the scaffold can be, so if I put into the scaffold and then they can be delivered to that particular defect, and then you can seal it. But when I inject, or when we do the injection of the MSC cells, it might be migrate towards a different area. So this is a problem when you don't encapsulate the MSC cells for this particular disease or these particular complications. So what we found, this is one of the animal model trial that we did. We also wanted to see whether the MSC can be transplanted directly without pre-differentiating to the chondrocyte, because cartilage is made of chondrocyte, or is need to be differentiated to the chondrocyte. So we do the autologous chondrogenesis, take the MSC and then differentiate to the chondrocyte and put them, this is alginate beads, so we capsulate them into the alginate bead, and then we put into the rabbit model, we do the focal cartilage defect, and we actually put this bead with the cells, and then to see what is the difference it's going to give us. Should we differentiate them, or we can actually inject the MSC directly? So this is what we found with the H&E staining when we do the histology. When you use the MSC alone, it does give you a good regeneration. So for example, like the safranin O and then H&E stain, you can see the tissue is regenerated, or is rather recap reseal the area that being defect. And the autologous, if you do the differentiation into the chondrocyte, it does not really give much of the differences between the MSC and the differentiated MSC. So that's indicating you could also transplant the MSC without differentiating to the chondrocyte, and it does give you the similar result. In fact, the autologous MSC does give you a better result because it's reduced the inflammation in that particular area as well. And that's compared with the no treatment, we don't really see the regeneration of the tissue at that point, and then the normal one is a comparative. So with that part, we know that we lost the tissue because of the injury, and we can actually use MSC to replace the lost tissue, and also the MSC produce all these factors to activate the tissue that remain in that particular site to be regenerated back. But again, people are looking at any acellular therapy, which is much more simpler, which can achieve this one. It would be a good strategy because you don't need to do the cell manipulation. As I said earlier, the aged patient might not going to have a very good MSC with the potential to regenerate. It might be like undergo aging. Therefore, this acellular approach is one of the good approach for diseases, but not all the diseases can go for the acellular. Acellular means things without the cells, but still able to regenerate back the tissue. So we started to look at the platelet-rich plasma. In fact, we start this project because we want to replace the serum with the plasma, the platelet-rich plasma, because it's provide all these growth factor for the MSC to expand it. So we started the project with that purpose, but we also found that injecting PRP without even the cells does help the osteoarthritis to some extent. So again, as I said earlier, the degradation of the tissue happen. But if we look at these parts where if the patient comes with a very early osteoarthritic symptoms or the stage, that means you still have the chondrocyte remain here. Because they started to degrade, but then you still have the remaining chondrocyte, which is, if you use a PRP ideally with a growth factor, they should able to induce or activate the chondrocyte here to proliferate, so it can be recap the tissue that is lost. But this PRP or the PRP technology cannot work for the condition where the cartilage is already damaged completely. For example, you don't really have a cells here, so no matter what you put the PRP, you won't be able to regenerate the tissue because there's no tissue left there. Right? So it's very case dependent. There's a different method available to prepare the PRP, but we use the PRP centrifugation method. And for our study, in vitro study and in vivo study, we actually pool the samples because it's like sometimes you can't get like too much of blood from one patient. So we just take the donor samples and then we pool the samples and we use them to test it for the in vitro culture. So either you use the pool samples or it's an individual, and then you can actually log the batch and then to see is the different samples actually, or different donor give rise to a different level of the platelet rich plasma. Maybe I skip this one. So there's lots of interest with the PRP in the sport medicine because, as I mentioned earlier, it cannot be total cartilage loss. It can be treated quite nicely for those actually very early or stage 1 of the osteoarthritic condition, as well as the sport medicine, because sometimes it's a very the defect is not really big and it can be regenerated back. So, and also the organization have approved PRP as a reasonable treatment without much of the ethical approval needed. And what we really, people reported on the platelet-rich plasma compared to the very conventional therapy we use, the corticosteroid, that the PRP supplementation is actually reduce the pain of in the osteoarthritic patient. They reduce the pain as well as it support to some degree they support the regeneration of the cartilage. And it's more efficacious than the HA injection, the hyaluronic acid injection, which is a very conventional injection that we actually supply to the patients to reduce the symptom and then improve the quality of the lives here. And they are quite effective in reducing the pain as well as the knee function, and they're also able to show a little bit better tissue regeneration when you use the platelet-rich plasma. Again, another advantage of the platelet-rich plasma is actually blocking the anti-inflammatory to facilitate, because inflammatory is one of the good process that needed for the tissue to recover after the injury, but too high inflammation or the extent of the inflammation is too high is actually cause the bad effect as well, because the tissue cannot be recover or regenerate better in this case. So this manuscript still actually the manuscript still under review. I just checked today whether is there any comments from the editor and the reviewer still under review. So what we propose here, either the PRP can be directly supplemented or just for the purpose of a concentrated delivery, we can actually put into the 3D scaffold either alone or with MSC, as I mentioned earlier. We also, because we started this project using the PRP to support the MSC proliferation, and we found in fact with the 15% PRP can support much higher, double the amount, the expansion of the MSC compared to the serum condition, and it provides the autologous advantage. So the growth factor from the PRP, which is relevant to the chondrogenesis, can now activate all the genes that are relevant to the chondrocyte and activate the cell proliferation as well as extracellular production. Because another area why PRP is one of the advantage here, they involve in the extracellular production to restructure or make the cells to be remodulated back and to reconstitute the tissue. And also when we use a PRP, they have some factors which can actually block the inflammation and the extracellular degradation, because this is what really happened in the osteoarthritis. When we have some injury, the inflammation being activated, the extracellular matrix degrade, and very often it's not the chondrocyte die because of the injury, but because the inflammation high, the extracellular matrix is degrade the surrounding tissue, and they sense it, something is wrong. These cells actually start to express all these apoptotic markers, and they actually commit suicide. this is all about the apoptosis. So this is how the osteoarthritis is actually progressed throughout the course of the disease. So just want to share a little bit on this is actually our the clinician, the medical doctors who are doing the master. They take a small project with us, and then they try out the wound healing and the skin rejuvenation using the PRP. So again, the same concept. PRP is actually shown to activate the proliferation. They activate the migration because they contain the migratory cytokine, and also they actually also reseal the wound, because in a normal condition the inflammation delay the epithelialization, but when you actually have the PRP, they activate the proliferation, therefore the epithelialization process is actually activated. And also we found that people reported that this is through the fibroblast migration, because you activate cell cycle related gene using the PRP, the platelet rich derived growth factor, and they activate the fibroblast proliferation, and subsequently they produce all this tissue regeneration over the injured area. So what is being found when we use, as I said earlier, PRP is wonderful, but sometimes it works quite better with the bone marrow derived stem cell. So what people reported here, your wound healing is much better in bone marrow compared to the control, but it's actually quite similar to the PRP. But very often when you combine the stem cell together with the PRP, they are actually activate or they speed up the wound healing, and also the closure of the wound is much faster. And if you see the wound closure is much higher when you combine these two factors. And this is through the remodeling of the extracellular matrix and promote angiogenesis, because angiogenesis is another problem where you have the injury and then you need to attract all these immune cells to remodulate back the tissue area and then remove any of the unwanted cells. But very often, this cannot be achieved, very effectively. But PRP help in inducing or promote the angiogenesis, and therefore the recovery. And this is topical application of the PRP. This is not our results, but it's more towards to recap. It is because of the acceleration of the fibroblast proliferation and also the tissue regeneration, so they can actually have the wound closure much faster, even if applied topically. So from our trials, when the students, this is because we also have the interest in the diabetic ulcer, because this is one of the quite critical complication in the Asian region country, as well as Malaysia. So when we actually, this is after 12 weeks of treatment using the PRP, but here we use the PRP together with honey and sugar. It's a combination that gives rise to a better treatment, because honey and sugar are well-known antibacterial properties, so they actually can reduce all these infection. At the same time, PRP can activate the tissue regeneration, and we found that the two patients that came to our clinics have a much more better recovery, which is they were suffering from the foot ulcer for quite a few months, actually much earlier, which is the conventional therapy can't achieve that one. And the other part that the student also take up as a small project is the skin rejuvenation. And this is again through the extracellular matrix production and activate the fibroblasts to produce all these collagen that reform the skin and rejuvenate the skin area. And some of the factors that present in the PRP, the PDGF, TGF, EGF, IGF, especially the IGF, because they activate the proliferation and all this protein synthesis, so they stimulate the skin regeneration, therefore reduce the wrinkles and rejuvenate back the tissue. And there's a couple of examples shows that when we actually use the PRP at 1, 5 and 10, and also by the way, I would like to point out here whether the PRP is activated before we apply or non-activated. It does not really matter, because we found that with the activated and the non-activated, they promote the similar tissue regeneration rate. So therefore, in our case, we usually use a non-activated for the cartilage repair. And here we found that with the 1, 5, and 10, you actually have the better at the 5%, but then sometimes not too high PRP will actually cause the higher proliferation. So this is where it's not too high going to be good, but we need to find which is the right and then amount that need to be applied for a better achievement over here. So this is another case study that the student did. This is about last year we published the paper. So this one is actually towards the skin, is a melasma, which is quite a refractory dermal melasma because it's of the pigmentation problems over there. So we treated the patient because more often the conventional treatment for this particular complication or the symptoms is actually the laser, the skin laser you use that. But then again, when you use the laser, the tissue is actually damaged, and that would actually cause the scar on the patient as well. So this one, we actually treat the patients with 2 times a PRP injection after 1 month intervals, and we found quite a good improvement on the pigmentation is reduced. But of course, because it's a human trials, we can't actually take the tissue to see the pigmentation level and so forth. So we actually would like to see whether that we can actually get more patients, because this is one of the students who actually had the clinic with the patient came over. So we decided to try just for the it's autologous, so it's safe for us. So they actually give a consent, and we found that after 6 months follow up, it gives a much better results actually. So how that's really work, as I mentioned earlier, when we do the subcutaneous injection of the PRP, and we found that ideally the PRP will activate the cells over here, the platelet component, which is activate the cells and then make the tissue to regenerate back, and they become remodel back to become a normal tissue, rather than the earlier you have this scar and the other particular problems here. And so I've come towards the end of the talk. So I put it up. One is a cellular based therapy, which is use the mesenchymal stem cell because of the advantage in a clinical application. And another one is an acellular, that means it does not involve the cells, but we isolate the platelet-rich plasma and then put it up for the tissue regeneration. But both achieve the tissue regeneration. And in my lab, I'm a scientist, so the clinician helped me with the clinical trials parts or the in vivo parts, and then we actually, as we know that so much of literature available on the stem cell PRP biology, we tested in vitro, we also tested on the animal, but clinical trials, I think it's the next things we need to pick up. As I think we were talking. I was talking to Steve yesterday. This is a part that I'm actually not familiarized. That's why the font size has become very small. I'm very familiar with this one, as many people actually quite know what it actually does and everything. Of course, we need to develop the protocol so that it's actually become approved. But this is a part that we need to focus, and that's where my interest is actually to come over here to learn from different speakers. Groups to see how we can actually move on, because I'm really not a business-minded person, and this is a part that is scary because I can't think like a businessman, but I think there's lots of people here that can actually guide us better. Alright, so that is where the future is actually holds a better promise for the PRP and the MSC cells. So this is part of my group. This is one group that I have it. The dental group is actually the other side. So we're working on the PRP and MSC in regenerative medicine. This is in collaboration with the orthopedic surgeon, the groups. And then my other interest is actually cancer and the chemotherapy targeting of the cancer stem cell, particularly because, as I mentioned earlier, I worked on embryonic stem cells, so they're quite similar with the cancer stem cell. So we're looking at the different signaling pathway and the different molecules that how to target the cancer stem cell, which is quite resistant to the chemotherapy. And my big passion is towards all these fundamental process, what really going on in the cells, so that you can manipulate your cells better. For example, we do look at the cell cycle, how the cell cycle can be manipulated so the cells, the MSC, because as I say, after passage 10, the MSC proliferation and the potential will be reduced. and we want to have like a better proliferation, so it can be expanded for the clinical application without losing the potential. This is one of the drawbacks or the challenge we have with the MSc, which is I'm quite sure if we're able to find some better strategy to expand the cells, that would be better. And also I'm working, as I mentioned before, I started stem cell work with the hepatocyte, and my entire group work on a neuron. So we do have a big portion of the groups was working on the neuron, and I was the only one working on the hepatocyte. I really enjoy working on that one because it's very difficult to differentiate into the hepatic lineage, but yet that so much can be improved and can be applied not only for the clinical application but for the pharmaceutical application. So because in the US and UK they have lots of demands for this one, because they have a program of reducing the animal usage as a model to test the drugs. So that is another reason why actually I went into the cancer, because I was working on the tissue engineering to remodel the 3D culture, so it can be mimicked to some extent as an animal model to test the drugs, and we can actually go for the reduce the amount of the animal that we use. At least it's cut down the amount of the animal, because we know that which one is working now for the drug efficacy. And these are our research facility available in my faculty, and it's actually I'm heading the central facility as well. So we have the proteomic facility, we have the genomic histology imaging facility, and we have the animal facility where it's a ALAC accredited lab. It's equivalent to the GMP accredited. Our cell culture, we are developing towards the GMP certification because of the requirement for the product development should acquire that one. And so these are my collaborators, and they're all those collaborators in UK. I was working on the neuron and hepatocytes, and with Pascal actually I worked on the amniotic fluid stem cell. That's again for the bone repair and so forth. And but I was working for all these groups for the embryonic stem cell parts. And in University of Malaya with Prof Kamaru, we are working on the orthopedic side of the application of the MSc and the PRP. Prof Ayati is where she's a dentist, so they supply us all the dental derived stem cell, and also Raja Alina, she's a physiologist, so she actually helped us a little bit on the tissue regeneration parts as well. And for the cancer project, most of my project collaboration is actually with the two groups here, Prof Fazlul from Michigan, and then Shrikant is from cancers. So we're working on the chemotherapy and then how to target the cancer stem cell with them. So, and the fundings are actually, we have some UK funding and the Malaysian government funding, as well as University of Malaya pumping some money as well for the research and translation. So with that, I would like to thank you so much for the time and the opportunity. I'm happy to take some questions.
Do you have any question, Dr. Birod, about her technique on hair transplant?
When you get a stem cell from the hair follicle, where do you get it from?
Oh, we buy it actually. We buy the hair follicle stem cell and we culture them using a different media.
When you buy, where do they get their hair follicle from?
From the human.
The hair follicle, they have a big structure.
Mm-hmm.
You have epithelium. You have
they actually go to the pulp of the hair, the pulp chamber of the hair follicle, and they take the stem cell from there. It's not the epithelial stem cell, it's not the epithelial layer, but it's actually the chamber of the hair pulp. So they take it from there actually.
They can be from epithelial stem cell, or from dermal sheet, or anteroot sheet. There are two parts, or even from fat. From fat, or may be very similar to mesenchymal stem cell that we have.
But this is actually, as well as the PhD student working on it, so it's not the epithelial type of the stem cell, but it's actually apparently derived from the, I think because when they actually isolate the stem cell from there, it's just like they look at the chamber, the part of it, the hair follicle part, and they actually isolate the entire region, which is not the dermal stem cell layer, not the other parts. So, but it's a commercially available one. So we are not very clear on how they isolated that part.
I think stem cell from hair follicle, we need to do more study.
Yeah.
We have to locate exactly where we can get the stem cell from. where is the stem cell and what type of stem cell, epithelium and mesenchymal, or even fibroblast. Fibroblast can differentiate to many kinds. I think even this mesenchymal stem cell that you talk about right now is one that can be derived from fat stem cell or mesenchymal stem cell from hair follicle, from the dermal sheath, from the outer root sheath.
Yeah,
I
sure.
have one question. When you talk, is when you use the hair, when you use the pulp from the hair root, okay?
Are you talking about the dental or the
We talk about different things.
okay.
Okay, when you talk about use the mesenchymal stem cell, when you get that tooth, missed out tooth, and when you inject to a body, is it a different person or the same person?
We haven't tried for the human yet. The dental pulps one we actually extracting from the patient and then we use for the in vitro, in vivo study. But the problem is actually we do aware that to make it autologous, it's going to be quite challenging unless we do the tooth pulp chamber, the stem cell from the tooth pulp can be stored, bank it, and then can be used for the later application, which is we just had the meeting with one of the company that storing all the stem cell to see what's the potential of storing the dental pulp stem cell and then for the future application. So that's one of the things we need to look into. At the moment we don't do the autologous, and we know that there's a challenge to do the autologous with that.
What's the definition of minimal manipulation? Does it fit with the minimal manipulation when we expand mesenchymal stem cells in vitro?
Expansion without any additional factors to make them differentiate?
We consider is a minimal manipulation, and we usually use cells anything between up to passage 10. That's considered minimal manipulation. But again, when we say it's up to passage 10, it's a minimal manipulation, or maybe some people do use for up to passage 20. But the problem is the proliferation reduced and the potential of the stem cell reduced. So therefore, we don't really want to use anything after the passage 10. So, but consider minimal manipulation. You take the cells, you expand them, and you put it back into the patient. That's considered minimal manipulation without any differentiation or any other treatment. We do that.
And the second question is, okay. Like the animal test, how do we check the mesenchymal cell when we inject back into the patient? How to check how much mesenchymal stem cell differentiate and become the cells what we speculated?
For the animal model, we actually do, because we inject the human to the animal, so we can actually use the staining to see how many cells is actually deposited. And this is how we found that more often the cells don't migrate to the tissue, injured tissue all, but they do actually ended up in lymph nodes, sometimes into the lung area, because they are stickiness of the surface. But for human, actually, it's quite tricky because you can't inject the animal cells into the human, so therefore it should be the human back to the human. And there is commercially available some dyes where we actually testing in the animal, which is they consider is non-toxic, can be used to track what are the cells with labeled with the dye, how many cells or how much is ended up in the targeted organ. Actually, that's one of the things is quite challenge for us. In fact, everyone feel that tracking is one of the things that we need to prove it, so we know how many cells can actually end up there. But you can choose to work on a different method of delivery, so most of the cells will be delivered to the area effectively. But again, it's not applicable for all the organs as well. At the moment, it's just we try to use the dye so we can track back the cells.
Any other questions? Okay, if not, I would like to thank Dr. Selvi for your excellent presentation. And I think the meetings such as today can bring in more research collaboration in the future. And I'm sure after this we will discuss about hair transplant project.
Yes.
But the most exciting one that I like to mention a bit about your liver project, because liver disease is quite common in Asia. And I think it's our role with ASEAN doctor and physician scientists to work together to help to combat for this liver disease.
Yeah.
Sure, I think this is one of the things I'm really looking forward. For the liver part, that's why I think you put your attention in quite a few things, and then as though I become a non-liver person now, because I have like only one project I'm doing with the liver at the moment, but I would like to expand that project and then try out with the MSc to see how that they can actually improve at least the markers, and then they can bridge the gap between the because liver has the capability to regenerate, but then we want to bridge the gap between the waiting time for the liver to regenerate by itself. But this is one of the things I look forward to. Thanks.
Okay, thank you very much.